So the first one we made Grignard next CO2. We're going to give the carboxylate and then the H plus work up the ACL to protonate that. So it's a Grignard reaction with CO2. Look pretty straightforward. Thionyl chloride converts this to the acid chloride, yeah. The amine reacts with the acid chloride to give the amide. Isopropyl amide, pyridine picks up the HCl that's going to be formed. Pretty straightforward amide reaction. Amide hydrolysis is going to open up this to give the amine and the carboxylic acid. It's going to be tough to get a neutral product because if you add acid to make this neutral, you're going to protonate that. But that's the neutral product. Most basic would be this guy here, sp3 nitrogen. The rest are not sp3. That one is less basic because the oxygen is pulling electrons away from the nitrogen, like a tug of war. Acidic conditions, first thing you want to do is protonate carbonyl. Nucleophile is ethanol. Add electrons up. We want to get the methanol kicked off and the ethanol remaining. So we want that to be a leaving group, so we transfer the acidic proton to there. Now we can reform carbonyl, kick off the methanol, and then the Cl can take the H back. And we would have the, we go from the methyl ester to the ethyl ester. But the O methyl bond is never broken, the ethyl bond is never broken. That's called a transesterification. We're going from one ester to another. But it's just basic standard carbonyl chemistry. How do we do? Okay, test on Monday. You need to make sure that these are pretty straightforward for you. If not, we've got a few more days. We need to move ahead, guys. We will be looking at this handout today, the yellow handout. In our outline, we left off, we were doing chemistry of amides. A primary amide, you can dehydrate it. If you remove water from a primary amide, what do you get? You actually get the nitrile. Okay, we remove 2 H's in the O. You're going to end up with a triple bond between the C and the N, and that's what you get. Dehydration for primary amide gives nitrile. You can do this with thionyl chloride or acetic anhydride. I started doing it with thionyl chloride. In the interest of time, because we need to get onto this yellow handout, I decided to put this on a handout. Everybody got the handouts from today? Here we go. Primary amide. You get the nitrile, you also get SO2 plus HCl. We showed that last time. First thing is remember the key resonance structure for an amide. Okay, and I showed you an NMR of this, of how the methyls on the nitrogen were not equivalent. Okay, lots of electron density on the oxygen due to the donation of the nitrogen. Also, what do we need to accomplish here? Which atom on the carbonyl carbon do we need to get rid of? The nitrogen or the oxygen? It's a triple bond here, right? There's the carbonyl carbon. Which atom do we need to get rid of? Oxygen. We don't need to get rid of the nitrogen. So first recognize that, right? How do we get rid of the oxygen? Well, this is what we're going to do. Consider this resonance structure. This oxygen is actually pretty nucleophilic of an amide. It can add to the sulfonyl, the sulfoxide, or the thionyl chloride. Electrons up, right? To give this sort of tetrahedral intermediate type. Electrons back down, kick off the chlorine. We can get the oxygen bonded to the sulfur by an addition elimination reaction. At this point, the Cl that gets kicked off could take an H there and make one of your HCl's. Pretty straightforward so far. We get to this point, when that takes an H, leave a lone pair behind, now the nitrogen's got a lone pair. Now, anytime a lone pair can make a pi bond and kick off a leaving group, that's easy to do. Have you ever said that? A couple of times. Is that oxygen a decent leaving group?
Yes.
It's not protonated, although we could, because we do have HCl. This is almost like a tosylate. It's an oxygen bonded to the sulfur, double bonded. Electrons in, kick off the oxygen there. What does that give? That gives triple bond between N and C, and the H remaining. Leaving group got kicked off. That's your LG. Of course, this thing, anytime you make a pi bond kick off a leaving group, that's easy to do. And so that's going to decompose down to SO2 plus Cl minus. Then Cl minus can take the remaining H, and you can get your nitrile, which is triple bond with a lone pair, and make another HCl. Hopefully once you see it, you say, wow, that's pretty straightforward. I see it now. Where originally when you saw the reaction, you're like, wow, how does this happen? Is there anything crazy there? Once you see it. Yes?
So you can work from any resonance structure, right? So you don't have to do that first resonance structure, even though it kind of ends up being longer if you do it from...
You don't have to, but eventually you'll have to do a resonance structure.
Right.
I could just react right here. Sure, you can react with any resonance structure. But eventually, then that's going to make that oxygen positive. Then maybe you do the resonance structure to make the double bond here and give the...
Yeah, that's what I
You do the resonance structure later. But resonance is how you get one of the pi bonds there. The other pi bond comes from the elimination of the oxygen leaving group. Yes, you can always work with any resonance structure. Other questions about that mechanism? Very fundamental stuff. Once you see it, hopefully you're like, okay, makes a lot of sense now. All right. You can also do that with acetic anhydride. You might try that on your own. Okay, very similar. So that's actually one way to make a nitrile from a primary amide. What can you do with nitriles? Well, nitriles tend to be very end products. The only thing we're going to do in this handout with nitriles is hydrolyze them back to carboxylic acid. Because any acid derivative can be hydrolyzed back to the acid, right? First off, it says, how do you synthesize them? Well, you can use cyanide. I mean, because you can take something like this, react it with like sodium cyanide, and that'll give the nitrile, right? That's just a standard SN2. Because cyanide is readily available. And we actually did that at the very beginning of this test material. Because we said what can we do with the nitrile? Let's go back. I think it's in this handout here. First page, yes. Right there. Same thing I drew on the board. Nope, that's not it. That's the Grignard. Right here, right? Nitrile? What can you do with the nitrile? What do you say? You can then hydrolyze it to the carboxylic acid. Okay? Finally, one of our new ways to make carboxylic acids. Well, now we're at the point of looking at this. Nitriles can be hydrolyzed to the carboxylic acid. So here we go. That's what B is right here. You can hydrolyze them with aqueous acid, or down below you can use aqueous base. Now, we're hydrolyzing, we're adding water. If you add water to a nitrile, what do you get first? You actually get the amide. Because what did we do on the previous reaction? We dehydrated the amide to the nitrile. Well, if you hydrate the nitrile back, you first get the amide. And you would hydrate it or hydrolyze it It's really not specifically a hydrolysis because you're not really lysing anything. You're not splitting anything off. But it's typically called hydrolysis. Give the amide. But amides can be hydrolyzed themselves. So you can continue on. Brackets mean it's not isolated, although sometimes you can isolate the amide. But if you continue on heating, the amide will be hydrolyzed to the carboxylic acid. And there you will split off the nitrogen as ammonia, or if you're under acidic conditions, ammonium. And we've already seen the hydrolysis of amides back at Roman numeral 6b. Now you can also hydrolyze nitriles using aqueous base. And there's also probably water here. Same thing, first get the amide, then you can go back to carboxylic acid. Of course, if you make a carboxylic acid under basic conditions, how's the acid going to exist? In the basic form until you add the proton, right? Okay, I've also put the hydrolysis on the handout on the flip side. Now, I went through the basic hydrolysis, and then below I just gave a few notes about the acidic hydrolysis. Do it under basic conditions, just like shown on the handout there. Let's begin. We've got hydroxide and water. What's the first step? Well, the first step is not protonating anything, because we're not under acidic conditions. We do have a strong nucleophile, though, hydroxide. The first step is hydroxide added to the nitro. Now, just like a carbonyl, which is polarized, I've drawn it sideways. Usually I draw it straight up. Why will a nucleophile add to the carbonyl? Because it's partial positive. It's polarized, and we can move the electrons onto the greedy oxygen. Well, the same thing with the cyano. Nucleophile will also add here, and we can move electrons onto the nitrogen. Okay? Now, which one do you think is more electrophilic, carbonyl or nitro? Carbonyl. Why carbonyl? Yes. Because oxygen is pulling more. So these electrons are originally pulled more, and so there's more partial plus here. Nitrogen doesn't pull as much, not as much partial plus there. So nitriles are not as electrophilic as carbonyls. Of course, carbonyl can vary depending on what the X group is. So usually, when nitrile chemistry requires like a little stronger heat, more time. But it can be done. Nucleophilic addition to nitrile. That's what we're doing first here. Hydroxide does nucleophilic addition. Nucleophilic addition. What do we get? We get this. What are we trying to accomplish? First off, we're going to get the amide, which has a C double bond O and a single bond to nitrogen. So we want one bond to nitrogen, not three. Well, this gives us only two bonds to nitrogen. Also, we want to put H's on the nitrogen, right? Okay. Well, this is a strong anion at this point. It'll take an H. Now you could take it from water and you can go completely neutral, or you can essentially take it from this oxygen here. We can call that proton transfer, and you can get this structure. Now, I said before you only do proton transfer with acidic H's. Well, that's a wee bit wrong. The reason we're able to do it here is because that's a very basic nitrogen. And so compared to this nitrogen, that is an acidic H. So we do a proton transfer. At this point, if we do resonance, we can make our double bond, which we need, to oxygen, put electrons over nitrogen. Now that nitrogen can take an H from water, and what do we then have? We then have our amide. Again, most of these mechanisms are pretty straightforward, but they're generic a little bit. That is, you can't memorize every step or you're just going to get mixed up. You just do what you need to. Basic understanding, move electrons correctly, some fine details, dealing with the proton, nucleophilic addition, resonance, dealing with the proton, amide. Amides can be further hydrolyzed. Hydroxide can then add to carbonyl, electrons up. At this point though, what would you do? That's not an acidic H. That's not a strong base. I would not do proton transfer here. This is a good point. What are we under, acidic or basic conditions? Basic. Usually when you're under basic conditions, all your charges are anions, minus. You typically don't want to make a positive charge under basic conditions. Of course, there's a positive sodium. That's a spectator ion. You don't want to have a true, one of your major species, a non-spectator ion, being positive. Everything's minus here under basic conditions. And if you look at acidic conditions, usually all your charges are what? Usually all those are positive. Okay? So, at this point, this is where you might have a question. Electrons down. Which is a better leaving group? Neutral nitrogen or neutral oxygen? Neutral oxygen is a better leaving group. Okay? But if the OH left, you would just go backwards. To go to the carboxylic acid, we got to get the nitrogen to be kicked off. And that's actually like less chance. So this probably sits here and goes back and forth most of the time, but occasionally one will come off and it'll go this way. So that's sort of a bottleneck, and that's why it makes it sort of slow. And nitrogen is reluctant to be kicked off, but you got to. Once you get it kicked off, you then have the carboxylic acid. The leaving group will take the H, because it's basic. Carboxylic acid is acidic. And this is your final, this is your end. Carboxylate and ammonia. Okay? If you want to get the H on there, you have to work it up with acid. Put in your strong acid, it'll protonate this. If there's any ammonia left, it will protonate that and make ammonia. I say left because a lot of times when you do this, you like reflux it for like several hours. And as the ammonia is formed, it'll just be pushed out of the condenser because it's a gas. And so it may not even be there at the end. And actually, as you're doing this, you can hold pH paper above the condenser and you can check for ammonia being released. A lot of times you just keep heating it until there's no more ammonia coming out the condenser. It means the reaction's pretty much done. Because you'll drive ammonia gas off with heat. That make sense? Okay, you can also hydrolyze nitriles with acid. Of course, the intermediate is the amide. The amide's further hydrolyzed to the acid. I'm not going to do complete mechanism, but what's the first step? Well, just like with under acidic conditions, you protonate carbonyl. You're going to protonate the nitrile. That makes the nitrogen want to pull even more. It makes more partial plus on the carbon. Now what's your nucleophile? Is it hydroxide? No, you don't have hydroxide under acidic conditions. You have to use water, a weaker nucleophile. Basically at this point it's just like above, except you have an extra proton. And so there'd already be an H here. There'd already be an H here. There'd already be an H there. And actually you would generate positive charges along the way. You should be able to do that on your own. Questions about hydrolysis of nitro? So, again, everything in the box, including nitriles, can be hydrolyzed back to the acid using either aqueous acid or, what does that say? Hydroxide. Okay, back to the top. Questions about the handout? expect you to be able to work through that and do it on your own. Okay? Just like in math, we've already done many problems, asking you to do one more on your own. It's very generic, basic stuff. If you have questions, please ask. Let's look at the back of this handout. Any questions? There's a number of miscellaneous handouts in here. I think this one's probably one of the more important. It makes a big important point. It's also a good application, particularly towards dentistry. Anesthetics. We talked about how acid derivatives, the reactivity of the carbonyl can vary depending on the X group. Acid chlorides versus esters, etc. That's mainly an electronic discussion. Chlorine withdraws electrons. The oxygen donates a net. Okay? Another factor that can influence the reactivity of a carbonyl is sterics. Sterics around the carbonyl. For example, let's just say, let me give you two esters. That looks funny, right? That's supposed to be a methyl. That's why a lot of times when you have just a methyl, you maybe draw an ME on it. That versus methyl ester versus a T-butyl ester. Would you say one of these is going to be more reactive than the other? Are both esters, are all esters the same reactivity? This is a big group, and while you may think it's over here, well, sometimes this group if we drew it down like this, could you draw it like that? Basically, you may say, hey, the nucleophile is trying to add. See, this group could be down like this. And what's going to happen? It'll run into some of that group. Okay? And it'll slow down the attack of the carbonyl. See, the methyl, if it was swung down, you see, it wouldn't be as much down here. Okay? So just because it's over here doesn't mean it can't swing down and block the approach. Okay. So that's where it's more of a steric effect. But sterics can also be important for attacking. And that's what this here gets at. Your anesthetics in dentistry, you have short-acting and longer-acting. And this is a common anesthetic here. What functional group is this? It's an amide. Of course, that H is not bonded to that carbon, right? Okay. But these anesthetics last until the body hydrolyzes that amide and splits it, hydrolyzes. And you get the acid and the amine. Okay? So they last, it all depends on the rate of hydrolysis. So they're all amide, so you can't say the amide is going to be hydrolyzed faster than the amide. What's the difference? The difference is these amides have different degrees of steric congestion around the carbonyl. Of these four, which amide looks most congested? Well, let's just look at these two here. Which of these two looks more congested? What's the bottom one? You see, that's just got a methyl. But this has this big, what, butyl? That butyl, it doesn't have to be drawn that way. It can be drawn this way and really block the attack to that carbonyl. Where this methyl is not going to block it as much. So you can make comparisons. What's the difference between these two? Which one's more congested?
Bottom one,
The top one.
Top one. You see, y'all can do this, yeah? You just gotta look at them, make direct comparisons. So one of them is going to last longer in the body and be resistant to hydrolysis. It'll be more slow to be hydrolyzed. And that's going to be a longer acting anesthetic. You shoot that into your gums, you're going to retard this for a week. Okay? Where the others may be hydrolyzed real quickly and just last 30 minutes. Now all these, they have to last a certain amount of time. Why do you think these two methyls are here? They all have that. See, these methyls sort of slow it all down. If these weren't there, they might get hydrolyzed so fast that the effect wouldn't last but 10 minutes. Then down below are some other anesthetics, like Novocaine. That's not an ambid, is it? What is that? Ester. Now, esters hydrolyze faster than amides or slower?
Slower.
Try? Yeah, try again. Esters react faster. We talked about the, okay. So Novocaine is inherently just a faster acting anesthetic. Or the effect is, say, faster acting. Not necessarily faster acting, but it's a shorter acting. That's the thing. Shorter acting, because your amides typically last longer. But of the two esters, which would last longer? Don't look at that, but that's basically the point. Sterics can also affect the rate of reactivity, right? Okay? In addition to the electronic effect. Okay, make it the yellow sheet. Any questions about erasing?
Will you ever be asked which is more influential, sterics or electronics?
It probably would be apples and oranges. It'd be tough to compare.
So we won't be able to.
Well, it'd be tough to answer, so probably not. Unless there was a question that I thought was easy to answer. Okay, yellow handout. Now this is in a little bit different format. It's sort of just written out as an outline in text. It's sort of just presented as just a series of reactions. Okay, we're going to start doing what's called direct additions. Well, not direct. Simple additions. Simple additions. The main mechanism for acid derivatives is what? Addition followed by what? Elimination. Of course, the proton transfer is often in there. Okay? Sometimes, though, we will only do the addition. Mainly whenever you cannot do an elimination. So let's look for that. We'll also have some new reagents. Here we go. We got this. We also will start doing some aldehyde ketone chemistry. This is a ketone. Sodium borohydride. What's the nucleophile here? Sodium borohydride is an H- source. We first saw that in organic 1 with oxymercuration. And H- is your nucleophile here. Okay? The boron has 4 H's. It's group 3. It owns 4 electrons here, so it's minus. And you got a sodium plus. This boron, you can't ever make boron happy. This is a solid. Some of you weighed it out in the lab already. The boron is like, hey H, I love you, but you and your 2 electrons take a hike. So it spits out the H and the 2 electrons. So it spits out H-, and those go and bond to something else. Lithium aluminum hydride, often designated as just LAH. LAH, well, aluminum is under boron, right? It's the same thing, except the cation is very commonly lithium. Not sure why it's the most common, but it is. One of these is a much stronger hydride source. Which one? Which center atom is maddest? Maddest being minus. The most electronegative or the least electronegative? The least. Which one is least? Do you have a periodic table on? Boron is on top, then aluminum. Which one's more electronegative? Boron. Boron's more electronegative. It doesn't mind the minus as much. The aluminum, being less electronegative, really hates the minus. It's like super mad. It's like, boom, I'm getting rid of you real fast. And okay, LAH is a stronger hydride source. LAH will cause fires because it will react with water, create hydrogen, and okay. Sodium borohydride is milder. You can use it with protic solvents. Okay, usually not a fire source. In terms of our reactions, they're both hydride sources. They give same products usually. So H minus. These electrons add to carbonyl. Electrons up. What do we get? Electrons up, and we have a methyl. What else is here? H. I'll draw it in. Down the road, I'm not going to draw it in. You have to know it's there and that it's a new H. Okay, what do you want to do now? What did we just do? Addition? What do you want to do now? Can you reform carbonyl? No. The answer is no. You're not going to kick off a plain carbon. You're not going to kick off the H that just came in. And you're not going to kick off like a benzene ring. Game over. You can only do the addition. And this is just called a simple addition. See, this is not an acid derivative with like a chlorine or an oxygen. And so there's nothing that can leave. So you can't do additional elimination. Acid derivatives, you do additional elimination. Aldehyde ketones, you just do addition. Only thing you can do is work this up with an H plus source, and what do you get? You get that alcohol. There's a new H there, right? I'm not going to draw it in.
Would this also be a good way of making
Go on over what?
making it a good nucleophile, starting material, a good nucleophile, if we wanted to add something to it.
Not following you. Ask me a little bit later. Okay. So show the product for number 2. It's the same thing.
Do we assume H plus what?
Good point. Good point. Assume excess reagent and aqueous workup. Okay. Where is the proton source? With sodium borohydride, you can use a protic solvent, and the protic solvent will supply the H. For example, you can do this reaction in maybe ethanol. And the proton will come from ethanol. Now, LAH, you cannot use an alcohol, you'll start a fire. Because that H minus will react with the H from the alcohol and you'll create hydrogen. So if you use LAH, you have to do the reaction first, and then you have to add in like an acid at the end. Okay? Product number 2 would be it'd actually be butanol, 1-butanol. Okay, H minus adds here, electrons up, boom, 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 electrons up, you get minus. How many H's now on this carbon here? There was 1 there to begin with, now there's 2. When this picks up an H from like solvent, or you add in H from an acid at the end, this becomes H, right? Here you go, it's butanol. Just because I drew it zigzag like that doesn't make it a difference. Okay, guys. Need you to work on these on your own, and we'll look at them on Friday. Number 3 is straightforward, except it's not a hydride, it's what? It's some other nucleophile. Down below, you will have a leaving group. Please do some work on these. We'll be hitting these hard on Friday. This is week 7 in lab, yeah?
Yeah.
Next week is last week.